So today's talk is by Professor Fang. A lot of the innovations from her research group, her lab there in City University of Hong Kong for this. A number of you probably quite familiar with Professor Fang. Just let me read out quite a number of things about Professor Stella Fang. Professor Fang is the chair professor in the Department of Electrical Engineering. She is also the director of the Center for Biosystems, Neuroscience, and Nanotechnology in the City University of Hong Kong. Professor Pan wrote a lot. She has already published over 400 technical articles, book chapters, invited presentations. And she's got many grants, and 13 grants already granted in nanotechnology and microsystems, with additional patents pending. Her research interest is the encompassing nanofabrication technology, biomedical applications, and MEMS technology, and also the other devices. Professor Fang achieved a lot in the field. That's why she is the fellow of the IEEE, ECS, AVS, Hong Kong Institution of Engineers, and also Hong Kong Academy of Engineering. So let's welcome Professor Fang to give us a talk today.
Thank you, Professor Wen. It's a very nice introduction that you have done. And thank you, Professor Lee, for organizing this tech talk for the Academy. So let me see if I can manage this pointer. It works. So as what Professor Wen mentioned, that the topic that I have today is quite broad. I cover different areas, mainly focusing on the nanotechnology, but we use it for different applications, whether it's biomedical or whether this could be some of the high-frequency devices or some of the matter devices. So a short outline of the talk. Those are the areas that I will cover. Among the different technology that we need to utilize for making nano devices, I will focus on one that is quite unique, so focusing on the Nanoimprint technology. And then we're going to have a few examples of whether they are biosensors or some of the biomimetic platforms for cell control, and some of the high-frequency devices for various applications, as well as some of the matter devices in the optical frequency range. So it's very nice that Professor Wen already mentioned something about my experiences. So that's where I am now at City University of Hong Kong, and I have been there for 12 years already. Time flies, and before that, that's where I used to be. I used to be at the University of Michigan in Ann Arbor, so I spent almost 20 years there, almost. And then before I joined Michigan, I was at MIT Lincoln Laboratory in Boston area, and that was a lot of fun. That's where I started my career. And these are different acronyms. I think those that may be familiar with IEEE, but the others are other technical societies that I often have close connections with. Nano. Why is that nano that we try to include so many different things? Because now nanos is in all different disciplines, they're all getting down to these very, very small sizes. Whether we are in the engineering area or physics or biology and chemistry, talking about devices, we are certainly into the nanometer range. And talking about the cells and biomolecules, even DNAs and atoms, they're all down to the nano area. So if we were to develop the technology, we can develop that for various applications, and that's the idea of it. And so in different disciplines that we are all getting down to dimensions that are a few nanometer range. I always like to start with acknowledgements because all this work that I'm going to go through very quickly really done by a lot of help from many people that we have. This is my research team at City University of Hong Kong. And of course, before that, I also worked with some of my colleagues in Michigan as well as in MIT, but no room to list everybody. And then, of course, these are my team members, and these are the collaborators that I have. After I joined CityU, those are the ones that I collaborated with recently. And we certainly do a lot of technical work, but then we also have fun. This is one of those hiking trips that we took with the group. And this group is a Stay Key Lab group, actually. That we have a Stay Key Lab in millimeter wave and terahertz area. So we also have a lot of fun with the different members. At City University of Hong Kong, it's a relatively small university, but still we have different facilities. We have what I call basic facilities, the clean rooms that we can use for nanofabrications. We don't include everything, but we include the key areas that we can do both micro and nano fabrication. So include both clean rooms in class 100 as well as class 1000 range. Basic equipment we have, but we don't have everything. So this shows that we have some of those basic equipment in lithography, etching, deposition, and metrology. If I want to do something small, nano, we first have to make the nano features. So patterning technology is critical. And these are the patterning technology, whether they are using photons for generating the patterns. Of course, if we use the photons like the Carl Zeiss aligner, you can go very small, maybe half a micron range. And then we do have the electron beam crested system as well as the Nanoimprint system. Now, I'm certainly biased, so I picked the Nanoimprint. The reason that I picked the Nanoimprint is because there are several advantages. Of course, one of the key things is that indeed we can use Nanoimprint to print whatever dimensions that we have on the stamp. So dimensions all the way down to 1 nanometer has been demonstrated. So it has the high resolution, but in addition to that, it has all these advantages of that we can do it fast compared to focus beam, electron beam or ion beam. And we can do it over a very large area easily. This is a 6-inch in diameter stage. So we can print the entire 6-inch nano devices all in one shot, right, in terms of seconds range. And then it can be very uniform, it can be very reproducible. But one of the unique features that other high-resolution lithography doesn't have is that it's relatively easy for us to produce three-dimensional devices. Three-dimensional because with the imprint technology that we can stack multiple layers together. If we can stack multiple layers together, then it goes from 2D to multiple levels of 3D devices. These are some of the older work that we do. When we first start utilize the nanotechnologies that we want to make either nano-electronic quantum effect devices or some of the photonic devices. So this shows that some of those in-plane gated quantum devices, electronic devices, or some of those distributed red refractor optical devices. And they all have the unique features that they are very small in the nanometer range. And often, though, we also need a very large height, depending on the applications. And so it's not surprising that we have something that has very high aspect ratio. And this is a field emission device. If you have a tip that is small enough, so they're atomically sharp, then the electrons, not necessarily they're confined within the semiconductor, they can emit out into the vacuum. So you create the electron source this way. So these are the electron field meters that you can build electronic sharp tips with what we call the self-aligned gate. and then also have some of those unique advantages. So it just demonstrated that initially when we build a lot of those nano devices, they are either, they have those quantum effect going from classical effect to quantum effect, and then they can be applied to electronic or photonic applications. Another area that we realized that we can also utilize the nanotechnology for is the MEMS system. So these are the MEMS system. MEMS system usually start with micro, but over time, as the systems and devices are developed, they also move from micrometer size to nanometer size. And this shows some of the a few quick examples of some of the very highly sensitive resonators. The resonators are some of those movable sensors that the sensitivity depends on the gaps between the place that we have. You see that those designs is that you have a lot of parallel plates, and then the sensitivity depends on how small a gap that you can make. So it's not surprising that we may actually make gaps that is only have a few tenths of nanometer range to increase the sensitivity, and we multiply all these sensors by having a whole array of those resonators, and then create the sensitivity that way. Or then this is the optical switching devices with the movable mirrors. So that's the uniqueness about MEMS devices, right? You have you utilize these electrical properties, but you also utilize these optical properties as well. And then on top of it, it has some moving parts. And here, then we show that once you can get the devices together, they become a lot more efficient and a lot more sensitive, and you can combine them together and build a portable system. This is the case where we can integrate the resonator sensors together with the CMOS circuitry. And again, all these sensors has the key features that they have very small gaps, but they have very large thicknesses. And this is to increase the sensitivity of the devices, and then the integration of the sensors, the actuators, and the circuits together on one single chip will make the functions much more extensive, but also the performance a lot better. And this is an example of a microsystem. MEMS is a microsystem. So we integrate a lot of components together, and this is a gas detector. And it's very small. It's all integrated together, portable, use very low power, but can detect a lot of chemicals at very, very low concentration, parts per billion. And of course, when you do that, then you need to utilize a lot of the technology. And as always, that if you want to increase the sensitivity, some of the devices, the structure that has very high aspect ratio, this is an extreme. I just want to show an example that when you go for such a high aspect ratio device, 80:1 in this case, 80 means that the height versus the width is 80 times. And now, a lot of people thought, oh, it's not possible to do it. But I always say that if you know how the technology works, you can always make it work. So, but the amazing thing is that with the integration of this device, we can have very high sensitivity detection of a wide range of chemicals at high sensitivity and much higher performance than what one can typically get. This is one of the examples. You see, those are the columns here. And you can, on a small chip, create a path for the chemicals to go through. And then this path that we create, because they can be so small and all integrated within, say, millimeter square type of sizes, that you can put miles of those paths there. And columns for chemical detection allow us to be able to very selective to separate out the different chemicals. And now I want to talk about the plasmonic sensor that really utilize the very small features of the nano features. And plasmonic sensors, based on the principle that we create some of the localized surface plasmon resonance field. So there's some of the enhanced electric field coupled together with the input source. And then depending on the microenvironment around the sensor, you can see that the resonance peak that is generated by the sensor will be shifted. And the nice thing about this plasmonic sensor is that it's very, very sensitive in the sense that we can detect very small peak shift. Most of the sensors, instead of utilizing the shift of the resonance peak, may utilize the intensity to detect what is in the environment. But using this peak shift, then you can get rid of all this noise that can be introduced related to the sensitivity of the detected signal. And so most people will utilize the plasmonic sensors in this way, what we call the 2D configuration, two-dimensional one. You can design the nano features in different shapes and sizes and arrangements. So that's typical. But what we did is that we make it, as I say, we have some way to make it three-dimensional, so why not make it three-dimensional? And because there's some advantages of doing that, once you do the three-dimensional layers, so here, compared to the conventional devices, now we have 2 layers of metal. Or we can even go further and stack more together and have 3 layers of metal. You can see that from the simulation of the electric field, the local electric field is substantially enhanced, and accordingly, you can have much higher sensitivity for the detection. And besides stacking multiple layers, like instead of 1 single metal layers, we do 3 or 4 layers. You can also create devices that are asymmetrical. Asymmetry actually also allows you to introduce additional excitation mode, dipole, quadrupole modes, and then that also not only enhances sensitivity, but it also makes the peak that has, the resonance peak that is much sharper. And that means that we can actually have a much higher sensitivity of detection, the figure of merit related to how sharp the peaks are. Then you can also be a lot more selective. So already this asymmetrical structure has a sensitivity of 650 nanometer per refractive index unit, whereas most of the 2D devices that one can get has about 200 to 300. And this shows the example of how we can apply to different applications that we may be interested in. We want to note that the plasmonic sensors not only that you can use it for detection of cells that are fixed or dead, you can actually use it in the fluidic system, use it for live cells. So this A549 is a lung cancer cell. So while the cells are still active and live, we can actually monitor it. And then these are the measured, what we call the extinction or the transmission through the plasmonic platforms. And then you can actually detect very, very low concentration of live cells as they move around. And then using also a very, very small volume of samples. And then the other side is that we saw that this micrograph here shows that we have some of those very, very small nano channels, right? What you see there, the green fluorescence parts are DNAs. DNAs are very small, nanometer size, and we try to get them into the nano channels. Usually, DNAs are coiled together. To get them into the channels, we have to kind of drive them through, and then the DNAs then can get uncoiled, and then we can detect that. To the extreme that we have done actually some work by specifically going into one part of the DNA and modify a particular site on that DNA. So that fluidic system really allows you to do a lot of very precise, very interesting modifications of the biomolecules. But what I didn't finish is that you can also use it to detect the DNAs, the selected DNAs with different concentrations. So this shows that those are the detection of the DNA at different levels. This is one more example that I want to show for the plasmonic sensors. This is not only 3D because you see that there's a bottom layer, and then the middle one is the nano holes, and then the top layer is the nano squares. So when you have such a structures that usually this is the top part is what you get. You get 3 layers that forms the plasmonic sensors, and but then what we're saying is that if you do something cleverly, you can systematically form a missing site. So that is the defect that we introduce intentionally. By the intentional created missing site, the defects, then they become a photonic crystal. So we're combining the plasmonic mode with the photonic crystal mode. And with that, the end result is that we have something that even has much higher sensitivity. And again, the uniqueness here is that we have 3D plasmonic devices. We create a very uniform defects at the designed location, and then form the 2 modes, plasmonic and photonic crystal mode combined sensor. And the advantage of it is that we could then generate a very, very high sensitivity. Remember, I said that most of the plasmonic devices has a sensitivity about 200 to 300 range. But this one goes all the way up to over 1,300 nanometer per refractive index unit, and also have a high figure of merit. So, and then this is actually a demonstration that once you can understand the technology that's needed to build different devices, you can utilize the different devices and then utilize our imaginations for the design of the devices and improve the performance substantially. And then with that, then there's all different designs that we can have, right? So we integrated the plasmonic sensors in different configurations. This is the one that has the highest sensitivity, the multi-mode plasmonic sensor. And then we can actually have the plasmonic sensor integrated with the fluidic system so that we can actually throw along some of those biomolecules along this detector. And if you have something that's very sensitive, we can detect very low concentration of the biomolecules, and such as the exosomes. Exosomes are some of those biomolecules that often are released during the from tumors. But usually in the initial stage, they have very, very low concentration. But if you have sensors that you can build different configuration to increase the detection sensitivity, then you can detect cancer at a very early stage. And then again, the more integration that we have in a system, then it become portable and it can be built at very low cost. We also said that utilizing the technology, then we can actually build different platforms that mimic what we have inside our body, mimic what we have in our tissue. And this is an example of it. Some of this that you see here is very similar to what we have in the tissue. Our tissue often have different structures. It consists of both the microstructure, so this big one here is mimicking the larger microstructures, but on top of the microstructures of tissues quite often has also nanostructures. And again, it's the technology that we can develop whatever we like. So we can integrate different things and make various feasible structures that to try to put it as a platform that is similar to what we have. This is a 3-dimensional platform that has 3 layers, bottom, the middle, and the top layer. So it becomes a scaffold structure. And you can use it, of course, whenever you have very scaffold structure, even this one, you can use it for for selectively filtering various biomolecules or cells around. And this is specifically trying to mimic what we have around our blood vessels. Maybe through the membrane of the blood vessels, sometimes the cells or biomolecules can pass around. And that's what we find that through the blood circulation, sometimes the cancer cells can circulate around our body. And then when it becomes, the cancer goes from one area of our organ to another one, it becomes metastasis. And so this is something that we try to mimic the membrane on our blood vessels, and this is continued passage of our the blood or the fluid around the body. So with that, an example of how we utilize it is that we can do live monitoring of how cells actually move along these different platforms. And the idea as our engineering thinking is that we build the different platforms that either consist of the micro or the nanostructures, and then we use it to control how cells move. And then while we are monitoring them live, so this is a live monitoring, for example, over time, so the cells are actually moving along our platforms. We can monitor the force. This is the traction force that we can measure while the cells are moving under different configurations. And then we, of course, that we can monitor the speed, how fast they move, and whether they're moving directionally or whether they are moving randomly. And of course, what we like to do is that most of the cases, they move randomly, but we want to be able to control them and make them directional. And then this is the case that where we can actually look at not only how the cells move, but we look at some of the very small extension from the cell membrane, the filopodia. Usually they're in the nano dimensions and very, very difficult to detect, but using our sensors, we can detect them. This is the case that showing how we can detect, these are the extension from the cell membrane. Because they are in the nano dimensions, and most of the detection of the cells or molecules, they are using the optical techniques. And monitoring something in the nano dimension is very difficult. We show it here because we are using scanning electron microscope to do that. But we can also use our plasmonic sensor. You can see that those sensors are at the bottom here. And sense those very nanometer-sized filopodia, which has a lot to do with how ripened the cell is and then how they move around in the tissues. And so the idea is that we actually separate out, this is the cell membrane, which is larger. The cell membrane is big in the micron range, but we separate out the micron-sized cell membrane from the nanometer-sized filopodia, and then using the micropulse, so micropulse to separate out the cell membranes from those extensions onto that when they extend that out onto the plasmonic sensor. And that allow us to sense the concentration or the number of the filopodia that we have for cells. And again, because of the plasmonic sensors that we look at, we want to emphasize that this is very sensitive. Even a shift of that resonance peaks all the way down to 1 or 2 nanometer, we can still detect them. This is yet another indication of how we use our biomimetic platform to monitor live cells. This is the nasopharyngeal carcinoma cells. Those are the tumor cells that we have in our nose, NPC. And it turns out that when they form what we call the infaetopodia, and those are the ones that shows the green fluorescence that you see in this video. They are the one that when they invade, what they mean by invading, that means that they can actually go through area that they should not be going through, right? We would like the cancer cells not to be so aggressive and go through everywhere, but turns out that the NPC has the infaetopodias that's being decorated by the green fluorescence here, that they can get through. They can get through the blood membranes and then circulate around to other parts of our body. And we can clearly see that with our generated engineered platforms, this is a simple case that we generate gratings that has different depths. And we see that those inflatopodias are formed along the edges of any steps that you created. And then the larger the step, and this is 1 micron versus 0.1 micron. When you have the topography that has a lot of ups and downs, then the generation of those inflatopodia is a lot more. So you can imagine that with that, then the cancer cells will become a lot more aggressive. So there's ways that you can actually do so that you can try to make the topography doesn't have as large a step to reduce the aggressiveness of some of the cancer cells. And then another thing that we did is that we say, okay, if I can control the cells, then maybe I can separate out the cancer cells from our normal healthy cells. And this is a study that we kind of saw that. We utilized the property of the cells that we have in the same tissue. So these are all the MPC-related cells, but the MP460 are the healthy cells, and the MPC43 are the cancer cells. So we can create a platform using both the physical constraints, the physical dimensions, as well as the chemical coating. It turns out that we also do some of the coating. This is the coating of the fibroactin. In combination of the physical design and the chemical coating design, I can separate out the green, the red bar. This long bar is for the cancer cells, MPC43, and the blue ones, which is not too many here, is the healthy cells. So I can build platforms that I can separate out and ask the cancer cells to go one way, and then the healthy cells to stay behind. So with that, and it's actually very successful. It's after multiple revision of the designs that we can have the separation efficiency that's over 99%. Why do we want to do that? Because then if we are able to do that, then we hope that we can treat the tumors having the concentrated cancer cells and not to damage the healthy cells. So that's one of the idea. And then you can do that with the combination of both the physical and the chemical designs of the biomimetic platform. And this is another one that we created some passing channels. The idea is that the cells always like to go to different places, and sometimes you don't want them to go around that much. We need to watch over the time. So we want to see how easy that is for cells to pass from one location to the other through restricted and confined channels. And so this is an example again, having different topography, and certainly we also look into the coating effect as well, that they will have different ways of moving around such platforms, such that if we generate a lot of the nanostructures in the platform, so like this one with the nano holes around, it turns out that they limit their movement in a sense that it's harder for them to pass from one side of the restricted channel to the other. Now we're changing to a completely different area, leaving the biomedical applications and now moving on to some of the high-frequency devices. So now we're going to terahertz. Nowadays, I know that people have been talking about 5G, which is what we are using. 5G, what that we are using is about, has a frequency of about 10 to 30 gigahertz. And then 6G, that a lot of companies announcing that we're moving to 6G now, then they would have the frequency of maybe 30 to 100 gigahertz. But then we want to go certainly a lot higher. So we say, okay, let's go for terahertz, a lot higher frequency. But because terahertz is still relatively new, So one of the major problems is not how we designed and how we build the terahertz devices, but it's how we test it. Because a lot of the testing equipments are not as well equipped to go into the very high frequency range. Design-wise and technology-wise, we can actually go a lot higher than terahertz here, that we saw here. But this is a design that we started very early on, and say that if we include open Westlands cavity with the antenna, then we can actually not only through the design drive it to very high frequency, to terahertz, from hundreds of gigahertz to terahertz range, but we could also increase the gain by having this open resonator. And one of the uniqueness of this open resonator is that it has a spherical cavity. It has a rounded, curved bottom. So of course, if we can do imprint, we can imprint anything, right? So if we can imprint, then any curvature or any sizes that we need to do, we can certainly do so. And so this shows the example of how we first demonstrated that some of those devices that we built with the open resonator antenna that is being tested at the terahertz range, and has a very, at that time, is a relatively very high gain of over 20 dB. And then say, once we can do that and say, okay, utilizing our technology, what else that we can do to also focusing on the high frequency devices, but and make it even better performance, the gain to be even higher. And this is the case that we use two sets of nanosurfaces. Bottom surface of the metal surface and the top set of metal surface. And again, what you do is that when you create this cavity here, we also can, one is that this design is for terahertz range, and then the other is that we can even increase the gain further at that high frequency. We also decided to use different materials, which is high resistivity silicon. Instead of using insulator or metal, we decided to use silicon to avoid the metallic loss, and then we still want to have very high gain. And still, this structure looks complex, but it's very doable. And with that, indeed, we can again measure the performance of this set of antenna design that has two sets of metal surfaces, and then have a gain that is even higher, up to 33 dBi range. And then in addition to that, the beam is very directive, very sharp. So now that we think, okay, we have that feasibility to do even higher gain and has a very highly directive beam, what else can we do is that we make it multifunctional. So this is yet another design, super heterodyne waveguide metal surface structures. So this is another waveguide metal surface structures that the unique things about that is that integrating the metal surfaces in a wave, coupling with the waveguide, we can actually allows more functions to be obtained. We used to say that, oh, I want to go for very high frequency and I want to go for very high gain, and indeed we have demonstrated that. But now I also can make it so that it would have adjustable output at different frequency. So this is an example showing that this is at 0.95 all the way to 1.05 terahertz. And then we can, by controlling the operation condition, that we can actually have the beam that can be output at different angles, at different directions. But not only that, if you actually continue to work on the design of the metal surfaces, you can actually have other things like focusing, changing the direction, and doing the frequency scan. using the similar ideas of combining the metal surfaces in multiple ways. And the nice thing about this is that because we are actually using some very simple structures to do those devices in silicon, so, and then it becomes radiative. So we can certainly, it's very compatible, and we can do a highly integrated designs, not only with the single components, but it could have multiple components that it can be all integrated together with low loss. Now, then I switch to yet another area that we say, okay, we can do all these three-dimensional nano devices, whether they are some of those nano pillars that we can stack them right on top of one another. This is the uniqueness about Nanoimprint. You can stack and build three-dimensional. And when you do that, you can control precisely all the dimensions, the pitch, the width, and these interfacial layers, and height, and so on. So with that, we have a lot of design feasibility. And not only that, we can rotate one layer against the other. Once you do the rotation, you can start to see that, oh, it's almost look like we're creating the moray patterns from that. This is with 0 degree all the way to 30 degree. You see very systematically, because imprint, we can do it over a very large area. So very systematically, we can actually see how we can change the moray pattern. And then we say, how can we utilize it? So it turns out that we actually utilize it to form what we call the twisted bilayers. And then it becomes some of those metal devices that we want to use it to control and manipulate the optical wave. And so this is how we stack the layers together. And on the left-hand side is the example of the nano hosts, the hosts that we stack on top of each other. And then on the right-hand side are the pillars that we stack on each other. You see that we can control the different dimensions, and the intermediate layer between the stack can be thick, or it can be super, super thin. It can be almost nothing. And then we can do different degrees of rotation with one layer against the other. So what we have done is that we use it to create the circular chromosome CD through these twisted layers. And we can actually create what we call the chiral magic angle. That's so on the left-hand side here. That means that you could actually control the propagation of the photonic waves and only allow the waves to propagate at a certain twist angle between these two layers. And then the propagation also is wavelength dependence. So we create some of those, what we call the magic angles. Those angles that where wave can be transmitted, whereas in other wavelengths that they cannot, they will be blocked. And then on the right-hand side is that using similar ideas is that we use it for imaging. So if we can actually have this chiral angle effect, then we can also use it to be able to image some of the features that, unless you are in the right configuration of the metal device that is being twisted at certain angle, then they will be visible. Otherwise, if you actually try to image it with the source that's coming at a different configuration, then they will not be visible. So we also use it for imaging this way. And one more that we think that we can do is that we go into what we call the non-local bound states in the continuum, the BICs. And then what this is that what we saw here is that usually when we try to build devices that we often have multiple layers, right? And then between layers that we have to have very precise alignment. And then how can we have nanometer precision of alignment is that we actually utilize the changes of the BIC as the as the angle actually got changed, or as the shift between the top and bottom layer got changed. And the shift that we're talking about could be very small. So if the shift is 110 nanometer, we can see a very large change in the resonance state. And then if the shift even is very small, we can still detect that, and then we can use it to figure out whether if we have multiple layers, whether trying to detect this BIC signal, whether the layers are properly aligned or not. So this shows that with the stacking or the nanoimprint, you can have quite precise control of the shifting, and then even with very, very small shift, we can actually generate. This is some of the shift is only a few. This one, some of the shift is only a few nanometer. One last topic that I'm going to go over. So I hope that okay, still have a couple minutes. It's another area that is also very small devices, so it's still metal devices space. This is what is called shape memory polymer, SMPs. And shape memory polymers has this characteristics that we just happen to use nanoimprint to print into the polymer. And then, so this is what you have right after imprint. And then you can add the condition that you want to bend the polymer. You can bend it to different angle, different degrees. And then, it has this memory. You remember what it used to be. And then under a given condition, it can be recovered. So in this case, the recover condition is that this is done by heating. It doesn't matter how we shape it at the intermediate state, but we can always recover that. So why would that be useful? What we could do is that we could actually use this to change the optical path of the beam, right? So if we have you have the photons, if you have a wave propagating through the device, that initially the nanostructures are in one direction, and then when we hit it, then it can be changed to a different directions. So you can see that then the beam coming in, and then it can be split into multiple paths, and then as it recover again by using the local adjustment, then the beam can be redirected into a different direction. So you can actually have this dynamic change of the optical path. So nowadays, what we would like to do is that not only that we can build the devices that can modulate the beam path, but then we also want to do one step further is to how we can modulate them dynamically. So that's it. That summarizes what we are going to talk about today. I talked briefly about some of the nanotechnology that we use, specifically the nanoimprint technology. And that has a lot of advantages, and one area that, one technology that we can use to build three-dimensional devices. And then we use a few examples. I know that I went through this very, very fast, so I didn't go into any details at all. And if any of you are interested in, I would be more than happy to talk to you more about it. But we use the different examples of the biomedical sensors, some of the three-dimensional platforms, how we can control and detect cells and biomolecules at very low concentration. We use it to go after some of the very high frequency antennas and lenses, and also build some of those metal devices with the nano features to control not only the electromagnetic waves, but also the photonic waves. And then some of those optical devices that we saw, including the one that we use the shape memory polymer, is that we use it to control the optical wave so that we can have changes of how the optical path can be manipulated, as well as whether we can use it to image for imaging. So with that, funding support, of course, from university as well as from RGC. And then thank you very much for listening, both for those of you who are here and for the online.